Welcome, everyone. It's a pleasure to speak here at Data Science Dojo. Would love for this to be an interactive conversation on this topic of building and maintaining high-performance AI. Just to give you a quick background on Truera, I used to be a professor at Carnegie Mellon University, and with my then PhD student, Shayak Sen, we did a body of work in AI testing, monitoring, and explainability. And some of that work was the foundation on which we started the company. And in addition, we also have a deep bench of expertise in enterprise AI with folks from Google and Visa and Microsoft and a number of other big tech companies and startups. This combination of research and enterprise AI practice are the two pillars that led to the creation of product and tooling that is now widely used. The talk today is about managing machine learning model performance, which is a huge problem in practice. For those of you who have been following the news in this area, in the last couple of years, there has been tremendous advances in the adoption of machine learning. And at the same time, with that, the problem of managing model performance and quality has also bubbled to the top as an incredibly important problem for us to get on top of. One concrete example of this was Zillow, which was using machine learning models to estimate the price of houses. And based on that estimate, they were buying and selling houses. And one of the things that happened last year was that as the housing market cooled down, the machine learning models did not keep up. They were overestimating the price of houses, and that led to a huge $500 million write-off, just showing the scale of impact that problems with model performance can have on the world. We have also seen tremendous adoption and usage of generative AI recently. I'm sure everyone has been following ChatGPT and that series and body of work, which has opened up the possibility of AI assistants, interactive AI assistants becoming more mainstream across enterprises and consumer applications. But with generative AI, there is also a concern that unless we keep on top of it, unless we have a good sense of where its blind spots are, what is it good at, where it is not going to perform so well, and keeping on track of that is a big part of ensuring that the promise, and I'm a big optimist here, of generative AI is realized in practice. There's numerous other examples in other areas as well, with fairness issues coming up, models degrading over time, not being sufficiently transparent, all of which bubble up to the top the importance of staying on top of machine learning models that impact the world in very significant ways. So what do people actually do in practice in order to ensure the performance and quality of their models? What we often hear is that as models are being built and before they're deployed, data scientists peer review their models, they A/B test their models, and once models are in production, they frequently retrain the models as well as have mechanisms for alerting when certain kinds of metrics related to model performance start degrading. These are all useful tools to stay on top of models, but as the world changes over time, they're necessary, but not sufficient to ensure that model performance and quality is maintained. Let me begin with the post-deployment state first, and then we'll return back to what additional pieces one may want in terms of data science best practices and tooling in order to ensure the quality of models throughout the entire life cycle of machine learning. So if you look at the post-deployment pieces, why is frequent retraining not sufficient? Because there are two big classes of problems that it does not address. First, model quality problems stemming from concept and data drift. One concrete example of that was the Zillow house price estimation failure, where the world changed in a way that the relationships that were originally learned by the model between the input variables and the target variable, which is the price of the house, no longer was sustained when the world changed as the macroeconomic condition changed. That's an example of what is called concept drift in machine learning world. A second issue is data pipeline issues, which are a very common source of model quality problems. For example, if you consider a model that is being used for pricing in a retail setting, if the data pipeline is broken in some ways and it's pointing to older product codes or some other features where the most recent data is not available, is not being fed into the model, that can cause model performance issues. Simply retraining will not fix the problem. Alerting by itself is also not sufficient. A common piece that happens in practice is that there can be too many false alerts coming out of alerting systems that can lead to alert fatigue. In addition, alerts can be useful in highlighting a source of a problem, but do not guide debugging, which is how do you actually go about understanding the root causes of the problem and how do you go from there to fix the issue. So these are some of the gaps in best practices, which, while useful and necessary, are not sufficient to fully stay on top of model performance issues. What I'll talk about in the remaining time are three technical approaches towards addressing these gaps. The first key takeaway will be around having methods and tooling to carefully observe and iterate on models in production to ensure that we maintain their quality. The second piece, and we'll do a deeper dive on that, is when you see problems, how do you debug? How do you root cause issues? How do you troubleshoot? And then readjust and improve the models before pushing them back into production. And finally, I will have a section on testing and monitoring of large language models, which are increasingly getting widespread adoption. Examples of those include the GPT series of models, as well as models like Llama and Bloom, on top of which lots of other useful downstream models are being built, like ChatGPT, and downstream applications as well, such as powering search and document summarization and sentiment analysis and so on. So those are the three main areas that we will go into in the remaining time. And one of the things I'm going to do is that after each of these sections, I'm going to pause and take questions. And actually, Nathan, maybe this is a good time to also see if there are any questions that have popped up yet that I should answer.
Yeah, I'm not seeing any so far, but sometimes it can be a cause of the delay on the live streams. I guess Hussein would like to know how to handle more false positive without oversampling. That might be something that you get into a little later, though.
Yeah, let me pick up that question as we go into the debugging section, because I'll give you a bit more context on it and we'll pick it up.
Sounds good. And Hussein, if you can take that question, if you could put it in the Q&A tab for me, that way we won't lose it.
Great.
All right.
Excellent. All right, let's get into the observe and iterate section. And by this, and this is fundamental one, a key takeaway from this session today, is that I want to discuss a four-step process for managing model performance. The first step is to monitor the models, by which I mean to track performance metrics and other kinds of model quality metrics such as drift and fairness and alerting at scale. There are some significant challenges, engineering challenges and technical challenges in making this work in practice at scale that I'll touch on. Once you have the monitor step in place and you find issues with models through alerting, reporting, and other kinds of mechanisms, you need tooling to quickly debug and identify the root causes of issues. Step 3 is to iterate on the models informed by an understanding of the root causes. This could involve retraining the model, making adjustments to data sets, and so on. And finally, once you have a new set of candidate models in place, you want to evaluate and test them, pick the best model, and push it into production, and then the cycle continues. Now, this workflow addresses the challenges of drift, data pipeline bugs, and actionable alerting that I was alluding to earlier as the area where there are gaps in the existing methods and best practices and tools. So let's look at a couple of concrete examples of how this might play out in practice in terms of addressing concept drift and data pipeline issues. So in this example, we are considering a transaction risk model, which is, let's say, processing fraud or credit card transactions and is alerting if the transaction is too risky. When this kind of model is being monitored, you notice a performance alert that is triggered as the transaction risk model starts, the risk scores start drifting up and crossing some preset threshold during COVID. By drift here, what I mean is the model score distribution. So higher the model score, the stronger is the indication of risk. And then at a distributional level on the new data in the early days of COVID, this segment of transactions are being considered more risky relative to some baseline, which was from the pre-COVID days. Now, tracking all of this at scale is challenging. You get an alert, then the next step is to understand the root cause of what is actually causing this increase in the risk score distribution. And there, leveraging distributional Shapley values, one can identify features that are driving drift, and one might discover that dining spend was a big contributor to the drift. At that point, you can drill down even more and have a sense of what's going on here. So in this particular context, the modeler who's in the loop and understands the subject matter here might observe that historically, when dining spend suddenly goes down, that used to be a robust predictor for risk, because it might mean that people's income is going down for some reason, and therefore they're cutting back on eating out. On the other hand, in the early days of COVID, people stopped eating out because they were concerned about health and safety, not necessarily because their income had gone down. So this is a classic example of concept drift, where the world changed and the relationship between the input variable, dining spend, and the output target, which is an indicator of risk, did not hold true anymore. What was true before in the pre-COVID days is not true anymore in the early days of COVID. Now that we know what the issue is, we can iterate on the model. In this case, you could drop the feature and retrain the model, and then evaluate the new model and compare it to the old one. You might find that the new model has a more expected model score distribution, and you push it into production. So that's one example. Another example is addressing a data pipeline issue. So in this case, you track production sales forecasting model at scale. The model shows drift and decrease in performance. As you drill down, you find that it goes down to a data quality issue, which is some sales data feed from an online marketplace silently changed the data format of an important feature for the model, and that was not reflected back. And because the feature is broken, the model performance went down. In this case, the iteration step will involve updating the data pipeline to account for the change, and then you test the updated model, the model returns to the expected performance. So this workflow, and I'll pause here for a bit to let this sink in, is that this workflow of observe and iterate addresses the gaps of both concept drift, issues with concept drift, and data pipeline issues. It also addresses the issue where alerts are not actionable, because here we are not just stopping at issuing an alert. There are these next steps that are informing debugging, understanding the root causes of issues, iterating on models, and evaluating them to ensure that the new model now is of a higher model quality. So it addresses the three key challenges that I highlighted earlier: addressing issues with drift, concept and data drift, addressing data pipeline issues, as well as making alerts actionable. So it's a significant step forward from the state of practice before this kind of tooling is in place. So that brings me to the end of this first section of the talk. Observe and iterate is extremely important in order to manage the performance of models. And while I'm focusing on performance and drift related pieces as concrete examples, there are numerous other machine learning quality metrics that one could track and update and iterate on through this process, including issues of fairness, issues of stability, keeping track of the explainability or conceptual soundness of the model, and so on. Good. So maybe this is a good point to take a pause again, Nathan, see if there are any other questions or comments that folks have.
I see a thumbs up emoji, so I'm guessing people are with you right now.
Great.
Um,
Excellent.
yeah, so I think
Good.
we can continue, and if any questions do pop up, we'll answer them in the next one.
Great. Sounds good. So I've now given you the top level view of this workflow with monitor, debug, iterate, and evaluate. The next section, I want to zoom in a bit more into the debug section and go deeper. So, and before I get into the debugging piece, I want to give you a sense of the tracking and monitoring step, since that will feed into debugging. So the first step of monitoring and tracking at scale involves tracking a number of different kinds of metrics across segments of users. So these could be performance metrics of machine learning models, such as accuracy and NDCG, drift metrics, such as difference of means and Wasserstein distance, could be fairness metrics like impact ratio and equality of opportunity. These are just meant to be sample metrics. The actual list in practice to be useful is significantly larger than this and is also customizable and extensible. Now, one challenge here is that when data sets are large and you have streaming data as well as batch data coming into a monitoring system, scaling is a significant challenge. And this is where techniques from streaming metrics and time series data stores are very valuable. In particular, with streaming metrics, one of the things you can do is that, let's say you want to track accuracy over time and you have 10 million records. It's possible to get highly accurate estimates of performance with, instead of using 10 million records, just a logarithmic reduction of that to, say, a few thousand records. And that power comes from using streaming metrics, combining some of the work on open source work in this space on Apache data sketches with specialized techniques that cover these kinds of machine learning model metrics. Another kind of building block here are time series data stores such as Druid, which have good support for aggregating time series metrics and data. Now, when the model, in order to ensure that you can identify where the model might be going out of whack, you can set thresholds and alerts on events, and then these get triggered when, say, the model scores are drifting a lot or accuracy is degrading, and then you want to go deeper and do the debugging. The debugging step involves leveraging root causes with distributional Shapley values. And the key idea there is, let's say the model score distribution is changing, much like in our previous example, where in the early days of COVID, the model score distribution was going up, risk scores were going up, credit transaction risk scores were going up. And then you wanted to understand what features are driving the increase in risk scores. So in this example, you can see similarly, there's risk scores going up, and the drivers here, the most important driver is interest rate, and it's contributing half of the risk score, or half of this score drift is because of this particular feature. This really helps with focusing and identifying root causing issues, because it quickly can help the data scientist focus on areas where the model, which is causing issues for the model. And that can be a significant superpower, if you will, as people go about maintaining and improving the performance of their models in production. And you can drill down even more and go one level deeper to understand what is the cause, the actual detailed cause of the problem. And I'll show a bit more of this with a demo to illustrate this. So let me now transition into this debugging workflow, which cuts across performance debugging, drift, fairness, and explainability. And I'll focus on performance debugging for the purpose, in the interest of time, one of these four pillars, and walk you through both a workflow for a stepwise process for thinking about or working through performance debugging of your models in practice, as well as a walkthrough demo to help you internalize some of these concepts. For the purpose of this walkthrough, I'll make use of Truera's testing and debugging free product. So you can also go to app.truera.net and sign up, and you'll get access in very rapidly in a minute, and you can play along with me to help you internalize these concepts if you like. As I go through this particular project, let me actually show you here. I'll walk through these steps and then show you how it plays out. So if you are going to app.truera.net, you will sign up with your email address and password. I'm already signed up, so I'm going to go to the login page and quickly log into this diagnostics or testing and debugging product. Everything you need to get started is here. So you can launch a quick start and get started here. You can create your first project with your own data sets and models. One other area that I encourage you to explore is this educational section on learning about these kinds of AI quality concepts. There's a bunch of tutorials here. I'm going to focus on the performance, model. If you are in the product, you can also see a video walkthrough, but let me just walk you through some of the key takeaways from this process. So this is a project. This project is a rental property price prediction model. It is predicting the price of an Airbnb listing, and the labels are the monthly price of the listing. So very simple regression model based on tree regression trees. And the goal of the model, the task of the model, is to predict the price of an Airbnb listing based on a set of characteristics or features of the model, such as where they're located, which city they're in, how many rooms does it have, and so on. Right? And it's based on this public data set, which you can also go and play with if you like yourself. Good. So what I want to walk you through is this four-step process of evaluating model performance, narrowing the problem scope, analyzing the root cause of a problem, and then that can inform how you mitigate the issue. So let's start looking at these steps through the lens of this tool. So you're on the homepage for the project. It has description of the problem statement, project nodes. There's also a Google Colab. If you're a notebook first data scientist, you can go to the Colab and play with it as well. This code repository, data sources, and so on. So it's a good playground for you to explore in order to learn more about this topic. Now, I want you to start with this model summary page. This gives you an overview of how this model is doing with respect to certain performance metrics. So this model was originally trained on San Francisco data from San Francisco, where Airbnb initially started, and then it was applied to new cities. In this particular case, we are focusing on Seattle. What you're seeing here are the results of testing the model for performance on San Francisco and Seattle. The test metric is one of either root mean square error or mean absolute error. The smaller these numbers, the better it is. The higher the error number, the worse is the performance. And then these test results are encoding how much error the model has in its predictions. Smaller numbers, recall, are better. And then there's a color coding based on some thresholds you can set to indicate whether it's in the acceptable range or not. So for this model, the threshold of error was set to about 100. Anything below 100 is good. So you'll see that on San Francisco, the model did well. It passed the test. It's in green. Whereas in Seattle, depending on whether irrespective of whether you're measuring performance with root mean square error or relative mean absolute error, both of these tests have actually failed. And that's why they're marked in red. Now these tests, if you go to the test harness section, you can actually adjust the thresholds, create your tests, and so on. That's something you can play around with. What I want to show you is that in this workflow, this is step one, where we are evaluating the model performance. We observe that the model accuracy on unseen data is lower than expected compared to the training set. It's not doing as well in Seattle as we want it to relative to San Francisco, where the model was trained. And that's why this is flagged as a performance issue that you may want to go deeper into and debug. So how do you do that? What are some of these debugging steps? So if you click through here, then it's reporting out. We have this explore, focus, debug workflow, and it's showing you that in San Francisco, the mean absolute error is like 47, which is pretty good, whereas in Seattle, it's much higher. And now you want to narrow down and understand the root causes of the problem. So you can focus in different ways using this workflow. First, you may want to narrow the problem scope and see, are there particular regions of the input data space where the model does poorly? This is a form of error region identification or error hotspot identification. And the goal here is to rely less on ad hoc processes and become more systematic and methodical in the way that you go about debugging model performance. So you can go to this focus tab and identify error hotspots, meaning areas of the model areas of the data space where the model is performing less well relative to the average performance. So you can see that there are some hotspots here related to amenities around cable TV and home type or minimum number of nights. Those are some regions. And then if you drill down more, you'll get more information about what those regions are. The final thing that you want to do, you can drill down more into these hotspots and try to understand what's causing these error issues and how to go about fixing them. You can also go directly to the debug tab and identify the features which are contributing to error drift the most. So in this particular example, you'll notice that the latitude feature, which is a geographic location indicator, has the biggest contribution to error drift. That's the reason why the model the biggest reason why the model is doing less well in Seattle relative to San Francisco. Now we can drill down more into this and go into the next layer of detail to understand what is it going on, what is it about latitude that's causing this problem. So if you look at this sensitivity plot, on the x-axis is latitude, on the y-axis is the contribution to error. So higher values in the y-axis is worse. We want the error contributions to be lower. In green is the San Francisco data, in yellow is the Seattle data. So you can see that this is a very bimodal distribution. There's no overlap between the two. All the San Francisco points are here, or all the Seattle points are over here on the right. Now that's already a red flag, because what this means is that the data on which the model was trained, the San Francisco data, has no overlap in terms of latitude with the Seattle data, which is the new data to which the model is being applied. So that is not ideal. Machine learning models learn concepts and relationships from training data, and then are applied to new data. Ideally, there is overlap between the two so that learned concepts can gracefully apply to the new data. So this is already a red flag, but we can look for more information. So if you scroll down, we can also look at the error rate. So if you look at along the x-axis is the latitude, y-axis is L2 error. So higher values are worse. Again, we want to be lower down on the y-axis. And you can see the Seattle error, the San Francisco error rates are considerably lower than the Seattle error rates over here. So it's not just that there is no overlap between the train and test data with respect to latitude, which was a red flag to begin with. Very objectively, we also observe that the error rates are higher on this new data as one might have anticipated because of this lack of overlap. Now, sometimes the overlap in error rates, the error rates being higher, could be an indicator also where the ground truth is, but you'll see the average ground truth is actually it's quite similar across the two places. So now this has given us enough information to perhaps get to the conclusion that maybe latitude is not such a great feature to work with. It's a geographic attribute. It captures a geographic attribute of the rental property, which is good. We do want to capture their geographic attributes, but it's one that does not generalize very well. So going through this process, what one might have. So we went through the evaluation process, saw the issues, we narrowed down the problem scope, and then when we went to the debug state, what we understood is that this error rate is being a root cause of this error rate is the latitude feature. And in fact, this is not a feature that generalizes very, very well. And therefore, one might want to think about mitigations that address this problem. So you could brainstorm about different mitigations, but one could be to not identify a rental property by its latitude necessarily, but by something else which is relevant from a rental property pricing standpoint. So for example, it could be distance from the city center, or it could be based on the neighborhood in which it is, because prices vary by neighborhood, and so on. So that's a concrete example of how a workflow like this could work. And what I've shown you is just one example of debugging common causes of model issues because of shifting data or labels from the training data, in this case, San Francisco, to the data on which the new data on which the model was applied, the data from Seattle. But there's a lot of other issues that can also cause model performance related problems, such as insufficient data or models, incorrect data, external changes, underfitting, and the model itself having a performance metric that does not reflect the true business KPIs. And again, this is just one example of one of our 4 pillars of performance, but I encourage you to go look deeper at these tutorials. There's a lot of useful content there related to debugging of machine learning models, walkthrough videos, and you can also play with the product for free with your own data sets and models, and learn and internalize and use this in your day-to-day work. So go to app.truera.net and try it out. So that brings me to the end of this section of the talk. I'm going to take a short pause here and see if there are any questions. Nathan, over to you.
We have a couple. I think I'm going to save one of them for the end. But this one is, can we use / evaluate your solution with our models?
Yes, you can do that. So if I go back to the product, so there are a couple of ways of doing it. One is you can just launch Quick Start and just get started from there. That'll help you get started. You can create your first project. So if you're comfortable with notebooks and the notebook experience, you work out of notebooks, you can just get started from here if you like. The other option is to go through the tutorial page, and you can pick one of these pillars, let's say performance, and then as you walk through the steps of the tutorial, it'll show you the different steps, and then there is at the end there is also a pointer to a notebook that shows you how to ingest your own data sets and models, and you can leverage that to ingest your own data sets and models. You can also look at the project overview page. The project overview page has this Colab notebook, and this Colab notebook has guidance on how to ingest your own data sets and models. Great question.
Okay, I'd say let's go ahead and continue from there, and any other questions we'll answer at the end.
Yeah, sounds good. Great, let me go back to my deck here. In the remaining time, I want to switch gears. So far, the walkthroughs were with tabular data models. And what I want to discuss next is what the shape of similar analysis and monitoring, testing and monitoring done with large language models, such as the GPT series of models, and as well as applications that are built on top of them. Downstream models like ChatGPT, or applications such as information retrieval and search and chatbots and customer support and so on that are getting widely built on top of these kinds of models. So one quick background slide on this is that these kinds of foundation models are now everywhere. There's lots of examples of large language foundation models such as BERT, Roberta, DistillBERT, GPT-3 from OpenAI, Lambda from Google, Bloom, and so on. And the way these foundation models and their downstream models work is that you first train the foundation model on some very large and broad data sets. So for example, BERT was trained on a good chunk of Wikipedia text. the GPT series of models was trained on pretty much the entire text in the internet. And this process of training does not require labeled data, because a language model is just given a sequence of text. It's trying to predict the next word, and then it just keeps repeating that to generate the whole sequence, right? So if you give it as input data science dojo has, then it'll predict some excellent meetups or something like that, right? Like that's how it works. Because it works in that way, you don't need labeled data. And so this whole step of training, this foundation model, it's called self-supervised learning, in that you don't need humans to be providing labeled data. And that's why you can apply this training step on really, really humongous corpus of text or images and so on. Once you get the foundation model, then there's a fine-tuning or adaptation step that lets you fine-tune it to specific tasks where the adaptation can use your own data to build a model for your specific tasks. So for example, if inside of an enterprise you want to build a question answering system, then you can take a large language model such as GPT-3 or GPT-4, and then you adapt it with your own data sets and models to specialize it, to fine-tune it so that it does a good job of answering, say, internal questions on various topics. And there's lots of, the state of play here is that the previous generation of models are extensively used in practice. So the BERT class of models have had 30 million plus downloads. And then there has been a tremendous uptake of the latest generation of language models, such as the GPT models. There's lots of use cases and customer analytics, search and recommenders, document processing, chatbots, and so on, as well as assistance for knowledge workers, such as writing marketing copy or sales reach outs or homework help, and so on. So this is a huge, huge development in the world, and there's tremendous, tremendous excitement and promise here of artificial intelligence, generative models, large language models becoming embedded into lots and lots of useful applications that form the very fabric of both enterprise and consumer-facing applications. So how do we go about monitoring large language models at scale? Similar to what we were doing before for more traditional models, you'll want to track certain kinds of model performance or quality metrics, where on the x-axis here is time, on the y-axis is some measure of the quality or performance of the models. And then you can, the red in this visualization, the red line is for one model, that's the text Da Vinci model. The blue line is for another model, the GPT 3.5 turbo model, which performs a little less well in this particular illustration, but it's also cheaper. And then when the model performance metrics are not met, you can get alerts, much like before. The key question, one of the key questions here is, what are these metrics? What does it mean for a large language model to have good quality or poor quality in certain kinds of responses? One key observation here, and we are calling this feedback functions, is that requires feedback from leveraging the feedback that we are getting from the users of these systems. So in particular, this is an example with ChatGPT, where the user might explicitly provide a thumbs up, thumbs down signal indicator to indicate that the model is either performing well, that the response was good, or that it was not very good. You can also do other kinds of analysis, such as sentiment analysis on prompts, like this isn't a great service, to figure out that the response was not good. More generally, what we are proposing is a notion of feedback functions, which can be used to monitor the model performance on an ongoing basis. And feedback functions can be implemented in a number of different ways. These are just two examples. You could even use other LLMs to implement feedback functions. So that's a key insight and takeaway, and we'll talk more. I'll be happy to go more detail. We'll have a blog post coming out shortly that you may want to take a look at to go deeper. And then when you can test these models by setting some thresholds, much like before. And when these tests or thresholds are not met, you can get alerts. You can also find failure modes by automatically clustering problematic responses with examples to identify new failure modes. So the model might not be doing well on short transcripts or long transcripts or some other kind of characteristic that helps. That's common indicator of why the model is not doing so well. And this whole process can be discovered and surfaced leveraging embeddings, which is a way of summarizing the inputs and internal representations of these kinds of models. So I know we are getting close to time. So what I want to pause with here is that we started off with this observing that one of the biggest problems in scaling the adoption of AI and getting benefit from it is ensuring that they perform well in production. And to do that, we need to have a methodology that goes beyond simply retraining these models and alerting to observing and iterating on these models. You monitor, you debug, you iterate, and then you evaluate the updated model before pushing it back into production. And that addresses some of the common gaps with dealing with data pipeline issues, concept and data drift, alerts not being actionable, and alert fatigue. And that's a key takeaway from today's session. The second piece, drilling down deeper into the debug stage, is that systematically debugging model performance, drift, and fairness issues rapidly is extremely important, and having best practices, education, and tooling around it. And I did a walkthrough to show you what might look like in practice for one concrete example, but this is repeatable across lots of different areas of machine learning quality. And finally, while these initial, the first two takeaways were illustrated with more tabular data and more traditional machine learning models like tree models and such, which are very, very widely used, we also saw the beginnings of how to carry over that kind of analysis around testing and monitoring to large language models as well, with feedback functions and embeddings. Thank you very much. Let me stop here. I will leave this QR code here for you to scan. You can also go try out testing and debugging of your own machine learning models with Truera at app.truera.net. Thank you very much.
All right, thank you, Anupam. We do have a couple of questions. I'm hoping this first one doesn't quite make sense to me, so I'm hoping after I read it, it's clear, but we'll see. So how will an environment or social unpredictable situation affect AI in data science? Was a mind-blowing idea. Thanks for the session. So I'm not sure what the question is there, but
yeah, I think what was probably what triggered that comment is probably the example I gave, where in the early days of COVID, when risk scores were going up for this transaction risk model, the root cause of it was that dining spend had gone down. And historically, when dining spend goes down, that's an indicator of risk, because income, it's correlated. It might have historically been correlated with income, and it's an indicator that someone's income is going down. But that wasn't the case in this particular situation. It was more of an unpredictable environmental situation, which is COVID. And because of that, the model performance degraded, and the relationship between input and outputs were no longer true. I suspect that might be the origin of that comment, and it's a very valid point to make.
Okay. And how can someone get in touch with you? Because I'm seeing some sales related questions. So how can someone get in touch with you if they have questions, about the capabilities of your platform, and maybe they want to learn more from an enterprise standpoint?
Yeah, you can certainly email me at anupam.truera.com. The other option is, let me just...
If you scan yourself here, or you can also email me, daniel.wibo@truera.com.
Yeah, if you go to truera.com, you'll see a sign up option here. You can sign up to use the product for free, or you can request a demo here by doing a get demo. But feel free to just email us as well if you'd like.
Okay, and I'm going to ask one more question. Does the platform support deep learning models, or are they only for supervised learning?
Yeah, it does support deep learning models. The free product that we have put out is focused a bit more on the more traditional tabular data models. But we also have support internally in other products that. So if you're interested in deep learning models, you can reach out to us, request a demo and such.
Thank you so much for being here today. And Anupam, I hope you have a good rest of your day. Daniel, it was great working with you for this event, and everybody else, have a good rest of your week.
Thank you very
Thanks,
much.
Nathan.